I have been getting some message that we are using many mathematics into it. But dear friends, honestly speaking, I'm trying to see that not too much of maths, etc. is used. More importantly, I'm trying to see how physically we understand what is happening or what is the physical interpretation, so that we get the holistic view of the whole airplane performance. And that is why whenever I am writing some expression, you will find I will be repeating those expressions, try to add more physical insight into this. Once you understand that, maths is not that difficult and you can correlate. If you see my last lecture, we have derived a relationship delta E required equal to minus Cm naught by Cm delta E plus minus dCm by dCl by Cm delta E into Cl trim. Try to understand this expression. What was Cm naught? Cm naught was pitching moment at alpha equal to 0. And who are the contributor for Cm naught? Primary contributor was tail. If I set the tail at a negative angle, setting angle, it will give a positive Cm naught. That is, if I put the tail like this, some setting angle I call IT. So as flow is coming like this at alpha equal to 0, this will have force generated downward direction, and suppose CG is somewhere here of the aircraft, so this will give a positive pitching moment, which is Cm naught. Right? What was Cm delta E? Try to physically understand this. Suppose this is the airplane and this is the horizontal tail and this is the elevator. Okay? Let's say there are wings, whatever it is. What is delta E? Delta is the elevator deflection. And how do we define delta E? Sign convention wise? This is delta E positive, okay, and delta E up, this is up, this is negative. This is the convention, okay? And this is generally, you'll see it is also denoted as down, D and down. So now tell me, if this is the horizontal tail, which is here, if I have deflected this downward, so I know delta E is positive by sign convention. What this delta E will do? This will change the camber of the horizontal tail, so there will be additional lift because of this at alpha equal to 0, and this lift will give moment about CG in a nose down manner, that is, it will go pitch down. So what is the sign of this moment? Nose up is positive and nose down is negative, so this will generate negative pitching moment. Okay? So we say for positive delta E, Cm is negative. Similarly, for negative delta E, which is up, Cm is positive. And we combine this and we say the sign of Cm delta E is less than 0. What is the meaning of Cm delta E? That change in pitching moment coefficient per unit elevator deflection only, everything other remaining same. Is it clear? So that is the meaning of Cm delta E. What was dCm by dCl? we are now expert by now. DCM by DCL is nothing but approximately you have seen it is minus of static margin. And what was static margin? We know static margin is minus of x neutral point minus x CG of the aircraft with non-dimensionalized with C. Clear? So this term is also known. What about CL trim? How do I physically understand what is CL trim? I told you, if the airplane is flying with lift equal to weight, thrust equal to drag, because we have taken cruise as our equilibrium. All these examples are assuming that cruise is our equilibrium. So lift equal to weight, thrust equal to drag, then CL trim will be 2W by S by rho V square. Clear? This is very well understood. And the alpha corresponding to CL trim, because CL we know, CL of the aircraft, I can write as CL naught plus CL alpha of the aircraft into alpha. So if this is CL trim, then corresponding alpha we refer as alpha trim. Every term is clear? So what is the understanding? If I want to fly at a particular CL trim, if my question is how much elevator I should deflect, what I need to know, what is the static stability margin of the airplane? 10%, 15%. I put that value 0.1 or 0.15. Cm delta E value, these are aerodynamic derivatives which are known. Once a configuration is there, you can evaluate, you can get from tunnel, but assume that these values are known. Cm naught also is known. So everything is known here. So you can easily calculate what is delta E required. But understand one more important thing. This is an expression, right? You go on putting CL trim, it will go on giving delta E required. But there is a limit. If I go on deflecting the elevator like this, there is an angle beyond which the flow will get separated. So it will not generate lift at all, or very small lift, more drag, which the flow gets separated. So that is the point where you say elevator is not effective. So we need to know, we need to constrain this. You say, oh dear friend, I have a limitation, so I can only control it to my best strength. So it cannot be any CL trim, it has to be a limited CL trim. This is one question. Second thing is very important, please understand this carefully. Now try to visualize the connection between control and static stability. So if I ask you, which part is our control part here? Naturally, control is the elevator. So this is our control part. Okay? This is the elevator control part, to be more precise. Which is the stability part here? Stability means what? I'm talking about static stability. And you know, DCM by DCL is the static stability parameter. So this is the static stability parameter. Okay? We want to build up a relationship between this and this, which we have done it. But now we want to add value to it and try to physically understand what is this gentleman doing. Right? Think of a situation, suppose DCM by DCL is infinite. Suppose, first case, DCM by DCL goes to infinity, means it is very, very highly statically stable, infinitely stable. What is the meaning then? How much delta E required you require? If this part becomes infinity, so delta E also becomes infinity. That means it also requires infinite elevator deflection. So what is the physics you are getting out of it? That if I increase static stability, delta E requirement also will increase. Right? Similarly, in a reverse way you see, if DCM by DCL goes to 0, you know what is this case? DCM by DCL goes to 0 means it is neutrally stable. That is, xcg is just on the neutral point of the airplane, so it doesn't have any restoring moment. So then what happens? Then it says delta E required just minus Cm naught by Cm delta E. It doesn't depend upon CL trim at all, which is typically of a neutral stability characteristics. But if I take these two extremes, which are physically not realistic, but it gives us a message. It clearly says, as I reduce dCm by dCl, as I make it less and less negative, in absolute sense, right? What I am saying is dCm by dCl, if it is minus 0.2, and in one case dCm by dCl is minus 0.1, then I will say this aircraft is statically more stable compared to this aircraft. But your algebra will say minus 0.1 is greater than minus 0.2. I am not using that. So you please understand this. If this is more negative, so I will say this is statically more stable from that point of view. Okay. So coming back here, what does it say? That if I go on reducing the static, that is, I go on taking the xcg of the aircraft closer to neutral point, then the requirement for delta E also will reduce, which we have seen. Just a few minutes back we did that. Suppose this is the aircraft at xcg1, and this is the aircraft at xcg2, which is statically more stable. Definitely, if I call it 1 and call it 2, which is having more negative slope at the trim at this point. Definitely, this one has more slope, more negative. So you could see that if I want to trim anything here at this point, this configuration requires elevator deflection to neutralize this much of negative moment, pitching moment. But if I am using aircraft with a CG configuration so that static stability is so high, then it requires elevator deflection larger, because this negative moment to be neutralized is larger because it is statically more stable. So whatever we have understood there, this expression tells us exactly the same thing. Is it clear? Okay. Now in textbook you will find this is represented as delta E naught plus d delta E by dCl trim into CL trim. So you could easily see that d delta E by dCl trim is nothing but this term. Okay? And before I go to this, let us see the signs. Cm delta E, you have seen the sign is negative. dCm by dCl for a statically stable, it is negative. So this is negative, negative, positive, and this negative sign sitting here. So sign of this is negative. Okay? What is the sign of delta E naught? You could say Cm delta is negative, Cm naught is positive. So this is negative, negative, positive. This sign is positive. This is clear? So let us try to physically understand or develop some feel closer to the pilot who will be able to understand rather than going into all these equations, etc., etc. Let us draw this. Delta E versus CL trim. Please understand, we are not plotting delta E versus CL. We are plotting delta E versus CL trim. What is the meaning of that? That should be very, very clear in your mind. Suppose I was flying here. This is Cm versus CL graph. I was flying here, 0.1, 0.2, 0.3, 0.4. What we are trying to tell delta E by dCl trim is, when I am changing trim from 1 to 2, how much is delta E required? When I am changing trim from 2 to 3, how much delta is required? So it is the change in the CL trim, not in the CL. Okay? That should be very, very clear. So if I plot it, let's say this is for XCG1. You could see here that this value is positive, so you have a positive intercept here for CL trim to be 0, and the slope is negative. Slope is negative. Now, how the slope will change? What is the slope? d delta E by dCl trim is minus dCm by dCl by Cm delta E. So you could see that if I assume Cm delta E to be constant, it doesn't change with CG location, then I can see that as CG is going aft, CG is going towards neutral point for a statically stable airplane, dCm by dCl value will become less negative. Okay? So the d delta by dCl trim also will become less negative as far as slope is concerned. Is this part clear? If this is constant, as the CG is, as XCG is going towards neutral point, that it is becoming lesser and lesser statically stable, then this value will also become lesser and lesser in negative number. Okay? Minus 0.1 to minus 0.05, like that. So your slope of this also will become lesser and less negative. So if it is XCG1, then for this is XCG2, where I am saying XCG2 is aft of XCG1, that means XCG2 is behind, is closer to neutral point. Now from here you could see again that if I want to trim this aircraft for a particular CL, and if I have got this CG configuration, then I have to give this much of elevator deflection, directly elevator required. This is delta E required. Now think yourself, if I am changing CL to another new CL, which is more than the CL where you are actually flying in this case, that means in CM versus CL graph, you have to connect it. Then you will understand very well. CM versus CL graph, it is like this. So this point is this point. Now you want to fly at this point, some other point you want to fly. This is what happens. This much of negative pitching moment will be generated. So to counter that negative moment, pitching moment, you have to give or generate positive pitching moment. And how will you generate positive pitching moment? By giving elevator, how? Elevator up, isn't it? Elevator up will give us positive pitching moment about CG. So from here I understand that if I want to fly from CL to a new CL which is more than the CL at which I was flying, I have to ensure that elevator deflection is positive because it has to counter this negative Cm. And what I am getting here? Here also I am getting negative delta E. And what is negative delta E? Negative delta E by convention is delta E up. Clear? Now see, if I want to change CL from a particular CL to this CL for aircraft having XCG1, which is very highly statically stable, then so much of delta E up I have to give. This negative means up, right? Now the question comes, do I have this much of limit? How long or how far I can stretch the delta E deflection? How do I decide that? Let us see. From delta requirement point of view, I am only talking, okay? You can generate infinite such number of CL trim I can fly. Please understand, when I say CL trim I can fly, that means there is also a limit how much speed you can get, okay? So, but I'm assuming that, let's say, that is well within the control, and I can have this CL trim, I can have this CL trim, this CL trim, but how much? The question is this. So how it is done? You should know what is the limit of elevator which can be deflected because beyond that the elevator will lose its effectiveness. So that number, let's say delta E max, and we draw a line like this. Okay? Once you draw a line like this, and once you have delta versus CL trim, it clearly tells you you cannot go beyond this CL trim. So this is the CL trim maximum. Beyond that, if CL trim is here, I cannot manage it with the elevator. This typically delta E max value for a conventional airplane, it is between plus minus 15 to plus minus 25 degrees. But there are methods to increase this by adding some add-on system, right? Okay. So I hope now the pilot is seeing this graph delta E versus this CL trim, and pilot knows I have to fly at this speed. Suppose CL trim is given to him, he knows correspondingly for that altitude what is the speed he has to fly for maintaining lift equal to weight. So from this CL trim, he knows how much elevator up he has to maintain to go for that maximum CL trim. And he has every intermediate point and he understands. But the designer should ensure that the solutions are available, so that pilot by iteration, he can find out that solution. Okay? Thank you very much.